Why does your bulb light up the moment you flip the switch? The answer lies in a river you can't see: electric current. Welcome to Physics Bible, where physics meets clarity. Today, we kick off our electricity series by decoding the invincible power behind every gadget: electric current. In today's tutorial, our main content centers on definition of electric current, which is the flow of charges, the symbol, the SI unit, and the direction. The concept of electric circuit, open versus closed. Types of current: direct current, DC, and alternating current, AC. The real-world analogy: electric current like water flowing in pipes. So what actually flows through wires? If you said electricity, well, not exactly. Let's fix that once and for all. You are here because you want to truly understand current electricity, and today we're about to untangle one of the most misunderstood terms in physics: electric current. Static electricity, also known as electrostatics, deals with electric charges at rest, while current electricity deals with electric charges in motion. So what is electric current? Definition: electric current is a flow of electric charges, mostly electrons, through a conductor. What are the triune components of this definition? Number 1, there must be electric charges. Number 2, there has to be a conductor that these charges will flow through. And then the combination of these charges in motion grants electric current as the number 3 triune component. What is the formula? Now, mathematically, we can represent electric current as the time rate of flow of electric charge along a conductor, such as a wire. So electric current is equal to the quantity of charge divided by time. So if you look at this definition, you realize that the given electric current is represented by letter I. The quantity of charge is equal to Q, and time is equal to T. If you combine this based on the definition, then I is equal to Q over T, which denotes electric current in motion is equal to the quantity of charges per time. So if you make Q the subject of the formula, it gives you current multiplied by time. Q is equal to IT, where Q is in coulomb as the SI unit, T is in seconds, and I is in ampere. The SI unit of current is ampere. Take note of that. However, there are smaller units of current, such as milliampere, MA, and is equal to 10 raised power negative 3 ampere. And then we have microampere, which is mu A and is equal to 10 raised power negative 6 ampere. These kinds of low currents are common in transistor radios and electric calculators. The instrument used for the measuring of current is called ammeter. Smaller currents are measured using milliammeters, while very small currents are detected by sensitive instruments called the galvanometers. The circuit symbol for ammeter, galvanometer, and voltmeter are as follows. Number 1, ammeter is represented by uppercase A, galvanometer G, and voltmeter V. Is that clear? These are the instruments we are using: ampere, milliamperes, and volts. So what makes current flow, or what makes charges to flow? Think of it like water in a pipe. The charges are like water particles. They need pressure to move. And that pressure is the voltage. In a closed circuit, this pressure pushes electrons from the negative to the positive terminal. But in physics, we define current as going from positive to negative. That's called conventional current. What are the types of current? Number one, direct current, DC. It flows in one direction only. For example, we have batteries. Look at the sine wave at your left-hand side. And then number two, we have alternating current. AC keeps reversing direction at equal time interval. For example, you can get that from your wall socket. Look at the sine wave at your right-hand side. The left-hand side depicts direct current, and the right-hand side depicts alternating current. You can see the waveform alternating from positive to negative to positive and to negative. For direct current, you only have positive waveform. Now let's explain each of the triune components individually. The first is a charge, the quantity of charges. You can see them in black colors like balls, tiny balls flowing through the metallic conductor or the conductor. The wire, you can see it. Then you can see the bulb is lightened up. So let's circle the charges. You can see them, the charges. Let's cycle them. Yes, then this is our conductor, the path at which these charges flow through. I hope you are following. This is to enable you understand that when charges, individual charges, are in motion, current is generated. Combination of charges in motion gives you electric current. And you can see our bulb is lightened up. This is our source, the battery, and then we have our switch, which is the key. You can see it being circled. So these are the triune components of this electric current. Now, if we zoom into this, you can see them, many of them, right, combined in this electric conductor. In this circuit, the effect of charges flowing gives us light. You can see it is glowing. Our load is the bulb. Altogether, our switch is the one by your right hand side, black in color. Then we have our EMF source, which is the battery, and we have our load being connected as the bulb. The whole of this is called electric circuit. Let's zoom into it. If you look at it, you can see individual charges, right? Positive charges flowing. Okay? You can see them. These are charges, a conductor. You can see the space. They can't flow outside the space. It has to be within the space. So the conductor, take it like the tar road where your car moves. The charges becomes the car in motion through the tie road. I hope you are following. So with this, the concept of electric charges has been explained. Let's quickly solve an example. Calculate the quantity of charge flowing through a conductor of current 10 ampere passing through the same conductor for 10 seconds. So solution, let's extract the triune components from this question. 3 in 1. Number 1, given. We're asked to find the quantity of charge. So Q is equal to unknown. Our current is given to be 10 ampere. Then our time, the triune component complete, is 10 seconds. So which formula are we going to use? Using Q is equal to IT, the second equation. Okay, then 10 multiplied by 10 will equal what? 100 coulomb. You can write 100 C. Okay, and it means coulomb. Take note of that. If you have questions, you can drop them in the comments. So as you look at this topic, you realize that the triune concept, number 1, think it. Electric current is the movement of charge. Then you have to solve it. You use I is equal to Q over T to calculate how much current flows. Then number 3, you own it. Next time you charge your phone, realize current is flowing through tiny copper wires, thanks to this very principle. So what are the quick recap from this topic today? Electric current is equal to the flow of charges. Electric current is measured in amperes, conventional current versus actual electron flow. And then here comes DC and AC. Don't forget that I is equal to Q over T, the triune component of today's topic, and our formula. If that made sense, hit the like button. Share this with a classmate who still thinks electricity is some mystical force. In the next episode, we'll wire up real-life circuit components, voltmeters, ammeters, and resistors, and show you exactly how to use them. Subscribe now. Let's build your physics foundation one episode at a time. Here is a quiz for you. List the triune components of electric current as discussed in today's episode. List the triune components of electric current as discussed in today's episode. Thank you and stay safe. Connect to our social media handles at Physics Bible, the Triune Physics, for latest update. Thanks for joining us. Stay equipped, stay liquid.